So, I need to address a couple of things really quickly. As you all are obviously aware, we didn't have class on Wednesday because the university was closed due to the weather event and all of that kind of good stuff. The date for our exam remains unchanged. So it'll be, I think, not this upcoming Monday, but the following Monday, if memory serves me correctly. So what we're going to do is I'm going to condense my 3 lectures on transient analysis down into 2 lectures, which realistically it was always 2 lectures to begin with. The third day was literally just working an in-class assignment and doing the lab. In order for us to quote unquote do the lab, I'm going to cover a little bit more material today and Monday, and then I'm going to do the experiment using some of the old equipment so that I can literally project the results from the oscilloscope and all of that kind of stuff up on the screens around the room. And then you're going to use me doing the experiment to do all of your data collection and all that kind of jazz by looking at what's going on. So I'll kind of walk you through it step by step as far as collecting the data, and then I'll leave you guys to do the associated math in your own time. So that's how we're going to make up our lost time and remain on schedule. I also need to go back and change the in-class assignment structure and all of that kind of jazz. So we're going to wind up not doing in-class assignment number, I think it'll be 15. I'll leave it up so that you can do it as just having an example of another problem and all of that kind of stuff, but we're not going to turn it in for a grade. And then I'll move the dates around to the in-class assignments and all of that kind of stuff to reflect what's going on. All right, so today we are going to cover the natural response of first order circuits. Hold on just a second. I think that auto smooth, I want it to be off. There we go. Yeah. Don't know how it got turned on. So, missed an I there. So let's first talk very briefly about what a first order circuit is. So a first order circuit is a circuit that contains a single energy storage element. So either a capacitor or an inductor. Now, technically, it could contain multiple capacitors or multiple inductors as long as it can be reduced down to a single equivalent capacitance or inductance. It will be considered a first order circuit. Okay. This series of lectures is all on what's called the transient analysis of these first order systems, okay? So let's talk about what transient analysis means. So transient analysis is really just the analysis of a system as it is undergoing a change, okay? So analysis of a system undergoing or experiencing a change. So for us, that means we're going to have something that changes in our circuit. Now, this is technically different than looking at an AC circuit, because in an AC circuit, particularly a sinusoidal circuit, the change is constant. It never stops changing. And so that's an entirely different bag of cats that we're going to get into later on in this class. What we're talking about is a system that is at one particular state, and then some event happens. We see a response, right? So we are going to see a changing current and or voltage, and then after some amount of time, the system stops changing again. So we're going to go from effectively a DC steady state condition to the transient condition in the middle where change is occurring to another DC steady state where everything has stopped changing. Okay. So let's start by looking at a circuit containing a resistance and an inductance. So we might have something like this. So here's some current source IS, and it's going to be connected to a switch, like so. And let's say that the switch is originally closed over here at position A, and then at some point in time, which we're going to call t is equal to 0, our switch is going to change states and close to position B. So the network that's connected to the switch position A might consist of a resistor R connected to an inductor L, like so. And I fully acknowledge that there's a resistor on the left-hand side of the circuit, but it's not going to actually contribute anything during the transient condition. So I'm not going to bother giving it a label or anything like that. Okay. And this resistance R is representative of an equivalent resistance of a network, and this inductance L is representative of the equivalent inductance of a network. So we're starting with something very small and simple, and we're going to expand out into more complicated circuits. But really, everything that we're doing here is so generic that it can be applied to literally any first order RL circuit that we're ever going to deal with. Okay. All right, so I am going to define a few quantities here. So this is going to be my inductor current, IL of t, which is what we're principally going to be interested in. And then I'm going to choose this voltage to be the voltage drop across my inductor. So the current is flowing into the positive polarity terminal. And this might seem a little bit odd, and I'll explain myself here in a moment, but I'm going to choose to express the voltage drop across the resistor with a positive polarity on bottom. And the reason I'm the reason I've decided to put the positive polarity terminal of the voltage drop across the resistor on bottom is because during the transient condition, after our switch has changed state, any current that's flowing in our inductor is going to effectively turn around and flow into the positive polarity terminal of that resistor, so that all of my voltage drops are going to look like a positive quantity with this particular polarity. Okay. All right, so we are going to look at this circuit at 3 points in time. Okay, so let's start with what's going on at t is equal to 0 minus, which is the moment before the switch changes. So at t is equal to 0 minus, we are going to make an assumption here that the circuit has been in this condition for a very, very long time, so that we're at DC steady state. So I'm going to put a note over here. DC steady state. And this is just to remind me to use the DC steady state equivalent of my energy storage element in my analysis. So in a DC circuit, an inductor looks like what? A short circuit. So we are going to draw this circuit with the switch closed at position A, and we're going to replace our inductor with a short. So with the switch closed at position A, this resistor over here on the left-hand side is open circuited. Here's my current source IS. Here's my equivalent resistance REQ. Here's the voltage drop across my resistance at T is equal to 0 minus. My inductor is replaced with a short circuit because we're looking at a DC circuit. Here's the current flowing through my inductor at 0 minus. And just for the sake of argument, here's the voltage drop across my inductor at 0 minus. So, could we analyze this circuit? Absolutely. Okay, so let's do just that. What's the voltage drop across my inductor going to be? Zero. Why is it zero? So it's the voltage drop across a short circuit, and the voltage drop across a short circuit is literally always 0 volts. So VL at 0 minus is 0 volts. We can do that by inspection. What's the voltage drop across our resistor at 0 minus? Zero volts, because the resistor is in parallel with that short circuit, right? So since the resistor is in parallel with the short circuit, if there's a 0 volt drop across the short circuit, there has to be a 0 volt drop across the resistor. Lastly, what's the inductor current at 0 minus? IS. So all of the current from that current source, IS, will wind up flowing through the short circuit that is representing the inductor, right? So since the inductor current is non-zero, what does that mean? Well, it means the inductor has some amount of energy stored inside of it, right? Because we know the energy stored by an inductor is 1/2 times the inductor value times the current squared. So if the current is non-zero, there is energy stored in our inductor. And that energy storage is what's going to drive what's happening during our transient condition, which we'll circle back around to in a moment. Now let's look at T is equal to infinity. So at T is equal to infinity, this is a long time after the transient condition. So effectively, we're looking at the circuit now after all of our signals have died out and settled back down to some DC value. So this is, again, going to be a DC steady state condition, okay? So at T is equal to infinity, or a very long time into the future, our switch is going to be closed at position B, and because we're at DC steady state, our inductor is going to look like a short circuit. So here's that resistor on the left. My current source is connected to that resistor now. And then terminal A is effectively open circuited. Here's my equivalent resistance and the voltage drop across my resistance at T is equal to infinity. This short circuit is representing my inductance. Here's my inductor current at t is equal to infinity. And here is the voltage drop across my inductor at t is equal to infinity. And let's run through and figure out what all three of those quantities are again. Okay. So at t is equal to infinity, what's the voltage drop across my inductor? Has to be 0 because the inductor is being represented by a short circuit. What's the voltage drop across my resistor? 0, because the resistor is still in parallel with the inductor. So if the inductor voltage is 0, the resistor voltage has to be 0. What's my inductor current going to be? 0, because it's not connected to anything capable of giving it any current, right? So at this point in time, t is equal to infinity. Effectively, our inductor has lost all of its stored energy. So whatever energy it had at t is equal to 0 minus, it has been lost somewhere. So the process of the inductor losing its energy is what's going on during the transient condition, and that's what we're going to mathematically figure out, okay? So for 0 plus is less than t is less than infinity. So this is the transient condition. So this is literally all points in time between the moment after the switch changed state until our transient condition is over. So I'm going to write this as the transient condition. Our circuit is going to look like this. Here's our resistor. Our switch should be closed at position B. Terminal A should be open circuited. Here's our resistance Req and the voltage drop across our resistance. And it's going to be a function of time because we're dealing with a range of times here. Here's our inductance. The voltage drop across our inductance and the current flowing through our inductance, right? So because we're dealing with a wide range of time, it's not going to be obvious what VR, VL, and IL are going to be, right? Because we're looking for functions here. So we're going to have to go back to our roots. And by that, I mean we're going to apply Kirchhoff's voltage law to figure out what's going on, right? So if I apply Kirchhoff's voltage law around that right-hand loop, what I get is that the voltage drop across the resistor plus the voltage drop across the inductor have to add together to be 0. KVL says sum of the voltage drops around any closed path must sum to 0. Right? So we can express the voltage drop across the resistor and the voltage drop across the inductor in terms of that inductor current I, because that same current is flowing through both of the elements, right? So using Ohm's law, we know that the voltage drop across the resistor could be written as Req times the inductor current. And the voltage drop across the inductor could be written as LEQ times the derivative of the inductor current with respect to time. So what we have here is a linear homogeneous first order differential equation, okay? Now I understand that probably most of you have not yet had Math 245, where we learn all about solving differential equations. So we are going to do it in a completely different way. We're going to do it purely by intuition, okay? So effectively, our goal here is to figure out what IL is based on this equation. So I have some constant value multiplied by my inductor current plus some constant valued multiplied by the derivative of my inductor current, and somehow these things have to equal 0. So effectively what I'm looking for is a function whose the function itself plus its first derivative needs to come out to be able to make 0. So what function and its derivative have the exact same form? An exponential function. So we are going to make an educated guess and say that our inductor current will be of the form A, where this is an arbitrary constant. We're going to figure out what value it has here in a moment. E to the st, where s is just some rate of decay or rate of growth for our exponential function, which we're also going to wind up figuring out here in a moment. Okay? So we're making a guess on what form our inductor current must have during the transient condition based on the fact that the math tells us we need something that has a derivative so that when I add the function and its derivative together, it might come out to be 0. That's purely how we're doing this, okay? So if I substitute this guess value back in, what I'll get is A times REQ e to the st plus SA LEQ e to the st is equal to 0. And now I need to figure out what makes this 0, okay? So I am going to do a little bit of rearranging. So I'm going to pull the A outside here. Here I'll have REQ plus S times LEQ, and then I'm pulling the E to the ST out over here. I've just really factored common things out, and I've broken it up in this way so that we can really consider this as 3 distinct parts, all of which could wind up making this sum look like 0. And then we're going to discuss what that entails, okay? So hopefully, very obviously, if A were equal to 0, this whole thing is 0. That is a solution, but it is a trivial solution, and effectively it's the solution for if our inductor never had energy, or excuse me, any energy stored in it at all at any point in time. So it's technically true, but it doesn't really match the situation that we have. E to the st can approach 0 if s is negative and we wait for a very long time, right? Because e to the negative something t is going to go toward 0 as time gets larger, which isn't going to make this thing 0 for all points in time, so that really doesn't help us either. So what we have to look at then is this guy here in the middle, what's called our characteristic equation, or our characteristic polynomial. And figure out what value of s will make that middle bit 0 for all points in time.
And if the S was negative, then it wouldn't be 0 for all.
Right, so yes, so the exponential bit there on the right-hand side can only approach 0, but it can never truly hit 0. So that's why we're looking to the characteristic equation in the middle. So what value of S will make REQ plus S times LEQ equal to 0? Negative REQ over LEQ, right? Remember that negative sign down here in the notes. So this is the eigenvalue of our system, a fancy word you'll hear in Math 245. It doesn't really mean anything to us, but if we look at the units of it, so resistance is measured in ohms or volts per amp, and inductance is measured in volt seconds per amp. So effectively, the volts in the numerator of the numerator cancel out the volts in the numerator of the denominator. That is wildly confusing. The amps in the denominator of the numerator get canceled out by the amps in the denominator of the denominator. And what we're left with is something that's measured in per seconds. So this is a frequency, effectively. Something measured in per seconds, I'm always going to call it a frequency. This is what's known as the natural frequency of the system because it tells us how our signals are going to exponentially decay in this particular system when there are no sources or anything that's forcing it to do something different, right? Because during the transient condition, our resistor REQ and our inductor LEQ aren't connected to anything but each other, okay? The source is completely disconnected. So this is telling us how our signals will naturally decay when there's no energy input into the system other than what it originally had. Okay. So we figured out what S is. So now we need to figure out what A is, right? So we have this relationship. Our inductor current, IL of T, is of the form AE to the negative REQ over LEQ times time. So we're going to figure out A by looking at this expression at T is equal to 0 plus. So our inductor current at T is equal to 0 plus is going to come out to be AE to the negative REQ over LEQ times 0, or AE to the negative 0, which is just A, right? So at the very beginning of our transient condition, our inductor current is just whatever value it had at T is equal to 0 plus. Well, conveniently enough for us, we know that the current flowing through an inductor cannot change abruptly, which means whatever current it had at 0 minus, which we can absolutely determine using circuit analysis techniques, is going to be the current it has at 0 plus. See how everything's tying together from what we were talking about before, okay? So we now have literally everything we need to analyze any first order RL circuit, okay? So generically, we know that IL of T will be IL at 0 plus E to the negative REQ over LEQ times time. I'm going to put a box around this. Now, I want us to go back to this diagram, Okay, so we figured out what general shape our inductor current is going to have. So with that in mind, what's the voltage drop across our resistor going to look like? So let me put this out here in blue, okay? So during the transient condition, the voltage drop across our resistor is just going to be our equivalent resistance times our inductor current. Because the inductor current, all of it is going to flow through that equivalent resistance by applying Kirchhoff's current law up here at this topmost node, right? So that means that during the transient condition, the voltage drop across our resistor is going to be Req times IL at 0 plus e to the negative Req over Leq times time. And Req times IL at 0 plus is literally just going to be the voltage drop across the resistor at t is equal to 0 plus. So VR at 0 plus e to the negative Req over Leq times time. Anybody have a problem with that? Literally, all we did was apply Ohm's law. What's the voltage drop across our inductor going to look like? Anybody have any thoughts on that? So I believe, and hopefully we can all see this, that our resistor and our inductor are in parallel. We all okay with that? So the polarity of the voltage drop across the resistor is opposite the polarity of the voltage drop across the inductor. So I believe that the voltage drop across the inductor is literally just negative the voltage drop across the resistor, which is going to be negative. Let me move this up so that I have room to squeeze in the other stuff. Negative VR at 0 plus e to the negative Req over Leq times time. Or we could express this as VL at 0 plus e to the negative Req over Leq times time. Right, because the voltage drop across, or negative, the voltage drop across the resistor at 0 plus is going to be the voltage drop across the inductor at t is equal to 0 plus. So what we've just figured out here is actually that if our inductor current is behaving with this exponentially decaying response, every other voltage and current and all that kind of stuff in our system is going to have that exact same exponentially decaying response as well, because Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law are literally going to force that to happen, okay? So we now have a methodology by which to solve for literally any quantity that we might be interested in by analyzing the circuit at 0 minus, analyzing the circuit at, sorry, let me scroll back up here. So if we know what's going on at 0 minus, we look at what's going on at infinity and 0 plus. This is literally all of the possible information that we could ever need to solve a circuit like this. So let's prove that by working an example. Find one here in my notes. Okay, so this is going to be our circuit of interest. We are going to have a 1 millihenry inductor over here on the left. Let's put a 1 kilo ohm resistor here. A 1 kilo ohm resistor here. We've got a switch in the middle of our circuit that is going to open at t is equal to 0. One kilo ohm resistor here. One kilo ohm resistor here. Sorry, I drew my arrow the wrong way, and I have it written down in this example the wrong way. Got worried there. And a 1 milliamp source over here on the right. And I'm interested in finding current flowing through my inductor as a function of time, as well as the current flowing through this resistor as a function of time, and just for the sake of argument, the voltage drop across this resistor as a function of time. Okay. So these are the three quantities that we are going to be interested in, which means these are the three quantities that we effectively need to be keeping up with as we do our analysis, okay? So let's develop a step-by-step procedure for analyzing these circuits, okay? Our first step is going to be analyze the circuit at t is equal to 0 minus, and I'm just writing this out here as a reminder. This is DC steady state. So we are going to analyze the circuit with the switch open, and the inductor is going to be treated like a short circuit. Okay. So at t is equal to 0 minus, our circuit is going to look like this. So here is the short circuit representing my inductor. And here is my inductor current at 0 minus. Then I have the voltage drop across this resistor. So this is VR at 0 minus, and this guy is 1 kilo ohm. Here I have an additional 1 kilo ohm resistor through which some current IR at 0 minus is flowing. My switch is open. Here's a 1 kilo ohm resistor. 1 kilo ohm resistor. And a 1 milliamp source. So this is just plain Jane DC circuit analysis. And so we can literally use whatever DC circuit analysis method that we feel comfortable with in order to solve for these quantities. So what would you guys care to use here? So yeah. So we could definitely do current division here. So effectively, what's being suggested is that we treat, let me put a dashed line here, right? So if we treat everything to the left of this red line as a single equivalent resistance, then we have a 1 milliamp source in parallel with a 1 kilo ohm resistor in parallel with that equivalent resistance. So we can use current division to find the current that's flowing into that equivalent resistance. And then from there, we could do current division again to figure out how much splits off and flows through this 1 kilo ohm resistor and this 1 kilo ohm resistor, which is very easy. It's just going to be half of whatever we got from our original current division. So that seems like a pretty reasonable approach. So just redrawing things right here for simplicity's sake. Here's the REQ we're going to have to figure out. I'm putting a prime notation here just to remind me that this might not be the equivalent resistance in my inductor current equation. And the reason why I'm saying that is because our inductor current equation and all that kind of stuff was developed for during the transient condition. And we are not in the transient condition right now. We're the moment before the transient condition occurs. So the resistance seen by that inductance might not be this REQ. And so I'm just trying to make that distinction so that we don't get too mixed up. So let's call this current here IX, and it represents the current flowing through the network to the left of the red dashed line in our original diagram. We need to figure out what REQ is. So I think that it is 1 kilo ohm in series with a parallel combination of 1 kilo ohm in parallel with 1 kilo ohm, which should come out to be 1.5 kilo ohms. Does anybody have any problem with that being our equivalent resistance by inspection? So using current division, we should be able to say, let me move this down a smidge, that IX is going to be 1 milliamp times 1 over 1.5 divided by 1 plus 1 over 1.5. Where 1 over 1 is going to just be 1, and I'm throwing away the units of kilo ohms because if everything has kilo ohms in here, then they all wind up canceling each other out anyway. Okay. So I'm going to throw this in a calculator because I'm too lazy to do it in my head. But I think it's going to come out to be 0.4 milliamps. See? So 1 over 1.5, 1 plus 1 over 1.5, 2/5 or 0.4 amps or milliamps. Okay. From this, IL at 0 minus must be what? Right. So effectively, all of our current IX is going to hit this network that contains two 1 kilo ohm resistors in parallel. So we should easily be able to see that that current is just going to split in half as it flows down each of those paths. So IL at 0 minus should be 1/2 of IX or 0.2 milliamps. From this, what's VR at 0 minus? So 0.2 milliamps is flowing into the negative polarity terminal of a 1 kilo ohm resistor. So 0.2 milliamps times 1 kilo ohm should give me 0.2 volts, and then it will have a negative sign because the current's flowing into the negative polarity terminal. So negative 0.2 milliamps times 1 kilo ohm comes out to be negative 0.2 volts. And then IR at 0 minus is also just going to be 1/2 IX, or 0.2 milliamps. Does anybody have any questions, comments, or concerns about all of the analysis that we did here at t is equal to 0 minus? Okay. This current IX is flowing into the network containing two resistors in parallel. It splits evenly, exactly right. All right, any other questions regarding our analysis here? Okay. So the next thing that we are going to do is we are going to analyze our circuit at t is equal to 0 plus. So this is the beginning of our transient condition, okay? So because our system is in a state of change, our inductor is not going to look like a short circuit. So we're going to figure out what it looks like here in a moment. Okay. So for now, I'm going to leave the inductor spot here blank. And we'll figure out what to do with it in a moment. Here is our 1 kilo ohm resistor across which we're going to find VR at 0 plus. Here is our 1 kilo ohm resistor through which we're going to find IR at 0 plus. So at t is equal to 0 plus, our switch has closed. So our switch now looks like a short circuit. Here's a 1 kilo ohm resistor, 1 kilo ohm resistor, 1 milliamp. All right, so now let's talk about what we're going to do with our inductor here. Okay, so we know that the current that's flowing through an inductor cannot change abruptly, or whatever value it had at t is equal to 0 minus, it must continue to have at t is equal to 0 plus. So that means that there is a fixed amount of current of 0.2 milliamps flowing down through whatever we put here. Does the voltage drop across the inductor matter? No, it can be whatever it needs to be, okay? So at this specific instant in time, our inductor is actually behaving like an ideal current source. It has some fixed amount of current flowing through it. It literally cannot change, because for it to change means that we would have to create or destroy an infinite amount of charge or transfer an infinite amount of energy. So I'm going to represent my inductor with a current source that has the same magnitude as the inductor current at 0 minus, as well as the same direction as the inductor current at 0 minus. Okay. So this is the circuit that we are going to analyze to figure out what's going on at t is equal to 0 plus. And I just want to remind you guys we are analyzing the circuit at a specific instant in time. So I am not saying the inductor behaves like an ideal current source during the entire transient condition, only at this exact instant, okay? So how might we choose to analyze things here, okay? Well, we know, let me write this down here. Here's IL at 0 plus. We know immediately that IL at 0 plus has to equal IL at 0 minus, or 0.2 milliamps. That's literally where the 0.2 milliamp source came from, okay? So using that information, what should VR at 0 plus be? Negative 0.2 volts, because a current of 0.2 milliamps is flowing into the negative polarity terminal of the 1 kilo ohm resistor. So this comes out to be negative 0.2 volts. All right, so now we need to figure out what IR at 0 plus is. Does anybody have any thoughts here? So just to give you a hint, there's an easy way to do this and there is a hard way to do it. Anybody see the easy way yet? Patrick?
How would IR still be the same?
It will not. That's not even needed either. This 1 kilo ohm resistor right here is connected in parallel to this short circuit, which means the voltage drop across that 1 kilo ohm resistor is 0, which means the current flowing through that 1 kilo ohm resistor is 0. Or we could do all the other crap that you guys talked about, which is a waste of time. So here are our three values. A minimal amount of circuit analysis needed to be done for this particular circuit. Anybody have any questions about where any of these three numbers came from? Brandon? So I'm going to say yes, but very slightly conditional. And so what I mean by that specifically, the inductor current at 0 plus has to be whatever the inductor current at 0 minus was. What if there was no current flowing through the inductor at 0 minus? There would have to be no current flowing through the inductor at 0 plus, which means we would put in a 0 amp current source, which is a fancy way of saying an open circuit. So under that specific thing, we will put a current source. We'll put an open circuit because it's just forcing there to be no current flowing, still maintaining the prior condition. It's just depicted slightly different. All right, so now let's analyze the circuit at t is equal to infinity. And I even hesitate to tell you this, this step isn't actually needed. Now, what we're going to talk about on next Monday, where we have sources that are effectively left connected to our first order networks, the analysis at t is equal to infinity will be necessary. But for a natural response system like the one that we're dealing with, we should see that all of our currents and voltages of interest are actually going to decay to 0 at t is equal to infinity. We'll see that here in a moment. Okay. So at t is equal to infinity, we're at DC steady state again, because this is a long time after the transient condition has died out. Our switch is closed and our inductor is going to look like a short circuit. So here is my inductor through which I have some inductor current IL at infinity. Here's my 1 kilo ohm resistor. My other 1 kilo ohm resistor. This is VR at infinity. This is, sorry, IR at infinity. My switch is still closed. One kilo ohm, 1 kilo ohm. One milliamp. So I truly believe that all of our quantities of interest in this case are going to wind up being zero. Let's explain why. Everything to the left of that dashed red line is in parallel with a short circuit. So the 1 kilo ohm resistor right here is directly in parallel with a short circuit, which means there's no voltage drop over it, and therefore there's no current flowing through it. So IR at infinity must be equal 0 amps. Okay. The 1 kilo ohm resistor up here is also in parallel with that short circuit, which means the voltage drop across that resistor is 0. If the voltage drop across the 1 kilo ohm resistor I circled in green is 0, then that means the current flowing through that resistor is 0, and the current flowing through that resistor is the inductor current because that resistor is in series with the inductor. So IL at infinity is also 0 amps. So we actually didn't learn any new information whatsoever here at t is equal to infinity. And that actually kind of makes sense because if we look back at our equations, at no point in time did anything depend on what was going on at t is equal to infinity. So this step is literally being put in here just so that we don't forget to do it when we learn the new material on Monday, where it's actually going to matter, okay? And we'll talk about the distinction between these types of circuits on Monday as well. So this step number 3, as it stands right now, we can completely ignore without any loss of information whatsoever. All right. Step number 4. Determine LEQ and REQ. So, and actually let me explicitly state during the transient condition. Okay. So, I believe very firmly that the equivalent inductance in this system is 1 millihenries because there is only a single inductor in the system, and it's a 1 millihenry inductor. So I hope we can all agree that by inspection, LEQ is just 1 millihenry. So not a lot of effort had to go into that, which is great. Now we need to figure out what REQ is, okay? So what we're going to do to determine the equivalent resistance during the transient condition is we are going to find the equivalent resistance as seen by our energy storage element, okay? So we're going to take the inductor out and look in through its terminals at a dead network, and whatever resistance we see is the REQ for our equation, okay? So finding REQ. My inductor is taken out of the circuit. So these open circuited terminals over here on the left are where my inductor was. I have this 1 kilo ohm resistor, this 1 kilo ohm resistor, my short circuit because my switch is closed during the transient condition, this 1 kilo ohm resistor, this 1 kilo ohm resistor, and then over here, I have an open circuit because I need to be looking at a dead network. And so my current source being turned off looks like an open circuit. So really all we're doing is finding the Thevenin equivalent resistance seen by our inductor. So what's that resistance going to be? So I've heard, I believe, 2 kilo ohms and 1 kilo ohm. Which is it? Now I've heard 1.5. So these two resistors that I've circled here, that series connection of 2 kilo ohms is in parallel with the open circuit. So they don't contribute at all. This 1 kilo ohm resistor right here is in parallel with the short circuit. So it doesn't contribute at all. So it's literally just this 1 kilo ohm resistance. So I'm at the short circuit. Yeah. Yeah, there. So the two on the right are in that series combination is in parallel with that short circuit in the middle. Thank you for that. Okay. So we know what REQ is. We know what LEQ is. We know what was happening at t is equal to 0 minus, which informed what was going on at t is equal to 0 plus. So we now have all of the information that we need. Okay. So step number 5 is literally plug stuff into our equation. So I'm going to introduce to you guys here a generic equation that is applicable for literally anything we're going to deal with in an RL circuit. Okay. So Y of t, where Y represents literally any voltage or current in our system, is going to be equal to Y at 0 minus for t less than 0 minus, and then it'll be Y at 0 plus e to the negative REQ over LEQ times time for t greater than or equal to 0 plus. So we now have a roadmap for any current or voltage for literally all points in time in our system, everywhere from negative infinity all the way out to positive infinity. We know how everything behaves. Okay? So using this generic equation, our inductor current is going to be, so what was our inductor current at t is equal to 0 minus? If I'm not mistaken, it was 0.2 milliamps. So this will be what it is for t is less than 0 minus, and then it'll be 0.2 e to the negative. So let's see, REQ was 1 kilo ohm. So 1,000 divided by 1 millihenry, so 1 times 10 to the minus 3, comes out to be 1,000,000 or 10 to the 6th t milliamps for t greater than or equal to 0 plus. And I'm just going to put a little note here that this 10 to the 6 is literally just REQ over LEQ. Expressing it as a single number makes it look prettier, which is why I'm doing it. The voltage drop across my resistor. So what was the voltage drop across my resistor at t is equal to 0 minus? Negative 0.2 volts, right? And at 0 plus, it was also negative 0.2 volts. So negative 0.2 e to the negative 10 to the 6th t volts for t greater than or equal to 0 plus. Lastly, IR. So it was 0.2 milliamps for t less than 0 minus, and it's 0 e to the negative 10 to the 6th t milliamps for t greater than or equal to 0 plus, which is the same thing as just 0 milliamps for t greater than or equal to 0 plus, which of course should make sense because for all time greater than 0 plus or greater than and including 0 plus, that resistor was in parallel with the closed switch. So we shouldn't see any current flowing through it. All right, so this was our first circuit that we analyzed using our procedure. This can literally be applied to any RL circuit. Okay. So for the time's sake, we are going to now move ahead and talk about a first order circuit that contains a capacitor and what that entails. All right, so let's consider that we have a system that looks something like this. We have some DC voltage source Vs connected to a switch. And our switch is going to open at t is equal to 0. Here we have some resistance that is representative of the equivalent resistance of a network connected to some capacitance, CEQ, that is representative of the equivalent capacitance of some electrical network. And this is the voltage drop across my capacitor. This will be the voltage drop across my resistor. Current flowing through my resistor and the current flowing through my capacitor. Okay. All right. So let's follow the same basic steps to sort things out like we did previously, okay? So at t is equal to 0 minus, the moment before our switch opens up, we are at DC steady state. And so our circuit should look like this. So here's our voltage source Vs, our switch is closed. Here's our resistor REQ. Here is our resistor current IR at 0 minus. sorry, my capacitor should look like an open circuit. So here's VC at 0 minus. Here's IC at 0 minus. I'm choosing not to worry about my resistor voltage because it's pretty obvious that my resistor and my capacitor are connected in parallel. So if I can solve for my capacitor voltage, I'm solving for my resistor voltage too. So that's just one less thing I'm going to have to continue to write down. So what is our capacitor current at T is equal to 0 minus? 0 amps, because it's the current flowing through an open circuit, right? So at DC steady state, the capacitor looks like an open circuit, which means there can't be any current flowing through it. What's the voltage drop across my capacitor going to look like? Do what now? It is neither of those things. It's Vs because the capacitor is in parallel with the voltage source. Yep. So Vc at 0 minus is literally just Vs because capacitor is in parallel. IR at 0 minus is going to be what? Vs over Req, absolutely correct. So once again, we have a situation where our energy storage element has some amount of stored energy, right? Because since the voltage drop across our capacitor is non-zero, the energy stored by our capacitor is non-zero. When our switch opens up, the capacitor is going to gradually transfer all of its energy to the resistor, Req, which is going to convert that stored energy into heat until we hit the end of our transient condition at T is equal to infinity, where all of our signals have died out. So we're not going to worry about analyzing things at T is equal to infinity because we know it really shouldn't do anything. So now let's just look at what's going on during the transient condition. Okay. So for 0 plus is less than T is less than infinity. So during the transient condition, our circuit looks like this. Here's our voltage source Vs. Our switch is an open circuit now. Here's Req and IR at 0 plus. Here is our capacitor, CEQ, our capacitor current, IC. Sorry, this shouldn't be at 0 plus. This should be as a function of time. My apologies. And then here is VC as a function of time. So if we apply Kirchhoff's current law, what we'll find is that the current flowing through our resistor plus the current flowing through our capacitor must be equal to 0. We can express both of those currents in terms of our capacitor voltage. So this would look like 1 over R times VC plus C times the derivative of VC with respect to time is equal to 0. And once again, we have a linear homogeneous first order differential equation. So let's guess that our capacitor voltage will be of the form AE to the ST, just like we did for our inductor current. If we substitute this in, what we wind up getting is A times 1 over R e to the ST plus SAC e to the ST is equal to 0. I'm going to pull out my factor of A. Here's 1 over R. Sorry, this should be REQ. CEQ. E to the ST is equal to 0. And so what value of S makes this always 0? Yep, so -1 over the resistance times the capacitance. Absolutely right. So -1 REQ CEQ. Okay. So we know that VC is then AE to the negative T divided by REQ CEQ, and we're going to find A just like we did before. We're just going to say what's going on at time T is equal to 0 plus. So VC at 0 plus is going to look like AE to the 0, which is A. Therefore, our capacitor voltage is VC for 0 plus times e to the negative T divided by REQ CEQ. So this is what our capacitor voltage looks like during the transient condition. Effectively the exact same thing, except that the rate of decay is set by the equivalent resistance and the equivalent capacitance here, as opposed to the equivalent resistance and the equivalent inductance before. Circling back around to this diagram, it should be fairly obvious that IR of T is just VC divided by REQ. So that's going to look like VC at 0 plus E to the negative T divided by REQ CEQ divided by REQ, where VC at 0 plus divided by REQ is literally just IR at 0 plus. And during the transient condition, IC is just negative IR, which will wind up being IC at 0 plus e to the negative T REQ over CEQ. So once again, if our capacitor voltage is decaying exponentially, then we're going to find that literally every other voltage and current in our system is also decaying exponentially. Okay. All right, so let's work an example that has a capacitor in it. But they didn't bring any, so we'll just make one up. Let's not make one up. Let's do the in-class assignment problem with a capacitor in it. That way I don't have to make one up. Let's see. So that's the inductor problem. So here's our capacitor problem. We have a nice answer here that we can check our work with. So we're effectively going to follow the exact same steps as before, except that when we get to step 4, instead of finding REQ and LEQ, we're going to find REQ and CEQ. Okay. Now, I want to point something out here. We're only asked to find this resistor current IR of T. That being said, we need to know what's going on with the capacitor as well. So even though we weren't explicitly asked to find it, we're going to need to pay attention to what's going on here, right? So the energy storage element and what it's doing is effectively dominating what everything else is doing. So even if we aren't asked for it, we still need to know it, okay? All right, so our first step is going to be to analyze the circuit at T is equal to 0 minus. I think analyze as a Z. At T is equal to 0 minus, our switch is closed and our capacitor is going to look like an open circuit. So we have, let's see, a 2 kilo ohm resistor goes here. 4 kilo ohm resistor goes here. 4 milliamp source. And then one kilo ohm goes here. And let's see, so the switch is closed before opening. So our switch is going to look like a short. 2 kilo ohms. Here's the IR of 0 minus that we're looking for. Here's the VC at 0 minus that we're looking for. So to me, the easier thing to solve for first would be IR at 0 minus. So how might we go about doing that? Current division, absolutely. Took a little longer than I would have hoped for, but that's okay. So IR at 0 minus is going to be 4 milliamps times, so in the numerator, we have 1 kilo ohm plus 2 kilo ohms. So I'm just going to put 1 over 1 plus 2. So that's the total resistance of the right-hand path. And then in the denominator, we're going to have 1 over 2 plus 4 plus 1 over 1 plus 2. So I think it's going to be 2/3 of 4. So that'll be 8/3 of the milliamp, which is 2.667. The voltage drop across my capacitor at 0 minus should be what? So our capacitor is in parallel with the 2 kilo ohm resistor that we know the current flowing through. So the voltage drop across the capacitor is going to be the same thing as the voltage drop across that 2 kilo ohm resistor on the right. So that should look like IR at 0 minus, that does not look like a 0 minus, times 2 kilo ohms. is gonna come out to be 4/3 of a volt. Anybody have any problems with the analysis that we did there? Wait a minute, 8 times 2 is definitely not 4. So the analysis is fine. My ability to do simple math is very much not. Okay, sorry about that. Yeah. 16/3 of a volt seems more reasonable. All right, sorry about literally not being able to multiply. What that PhD will do to you. All right, step number 2, we're gonna analyze the circuit at t is equal to 0 plus. So at t is equal to 0 plus, our switch has opened up and our capacitor is no longer at DC steady state. So we're gonna have to figure out what goes on there, right? So with my switch opened up, effectively, I have this network over here, 2 kilo ohms in series with 4 kilo ohms. Four milliamps, 1 kilo ohms open circuit, 2 kilo ohms through which I'm trying to find IR at 0 plus. And then over here on the right is my capacitor. So we know that the voltage drop across a capacitor cannot change abruptly, which means VC at 0 plus must be whatever VC was at 0 minus, or 16/3 of a volt. So what I'm going to do is I'm going to replace my capacitor with a voltage source that has the exact same magnitude as my capacitor voltage and the same polarity as my capacitor voltage at t is equal to 0 minus. So what should IR at 0 plus be? Yep, so 16/3 is a VC at 0 plus divided by 2 kilo ohms comes out to be 8/3 of a milliamp. For time's sake, we're going to skip step 3 because it's just going to give us zeros for everything anyway. So now let's go to step 4. Find REQ and CEQ during the transient condition. And once again, we have a situation where there's literally only one energy storage element. So CEQ should just be 300 microfarads. To find our equivalent resistance, we're going to find the resistance seen by our energy storage element. So this is a Thevenin resistance. So we're going to take our capacitor out and look in through its open circuited terminals at a dead network during the transient condition, right? So here's my 2 kilo ohm resistor on the left, my 4 kilo ohm resistor. I turn off my current source by replacing it with an open circuit. Here's my 1 kilo ohm resistor. The open circuit from my switch because during the transient condition, the switch is opened. Here's my 2 kilo ohm resistor. Here's my open circuit where my capacitor was. And I look in through the capacitor terminals. What do I see? Two kilo ohms. So 1 over REQ times CEQ is 1 over 2,000. Let me do 2 times 10 to the 3 volts per amp, because that's what an ohm is, times 300 times 10 to the minus 6 farads, where a farad is an amp second per volt. And if we look at the units here, volts cancel, amps cancel. And so we're going to have 1 over 2,000 times 300 times 10 to the minus 6. 5/3 per sound. Step number 5 is just plug stuff in. Camden, you have a question? So VC or as a function of time. So VC at 0 minus was 16/3 of a volt. And then we're going to have 16/3 e to the negative 5/3 t volts for t greater than or equal to 0 plus. And the thing that we were actually asked to find, IR. So IR at 0 minus was 8/3 of a milliamp. And then IR at 0 plus was 8/3 of a milliamp. So 8/3 e to the negative 5/3 t milliamps for t greater than or equal to 0 plus. All right, so I've worked an example of an RL circuit and now an RC circuit. Talk to you guys about all of the steps and all that kind of jazz. So for the next 15 minutes, because that's all the time that we have left, I'd like for you to work on problem 1 and problem 3 of the in-class assignment, since we just did problem 2. If you have any questions about anything, I'd be more than happy to answer them. All that kind of good stuff.